Here we're going to work out a couple examples of the material we covered in lecture 12 here. Okay, first example. Henry's law constant for CO2 dissolving in water at 25 degrees is 29.4 liter atmosphere per mole. What is the molar concentration of CO2 in the solution if the pressure above the solution of CO2 is 2 atmosphere? This you might recognize as a Henry's law problem, primarily because it says the Henry's law constant. So let's do this. Remember that I said there are a couple ways to express Henry's law. One was to make pressure proportional to concentration with some Henry's law constant, and the other is to make concentration proportional to pressure with some other Henry's law constant, and we could tell the difference based upon the units of the Henry's law constant. Well, we look at here, this is 29.4 liter atmosphere per mole. And let's just write that as 29.4 atmosphere per mole per liter. All right, so this looks like you have to multiply by concentration to get pressure, multiply by concentration to get pressure, so we're going to use this. So we're asked to calculate what the solution concentration will be if the pressure above the solution is something. So the pressure above the solution in the problem is 2 atmosphere. The Henry's law concentration or Henry's law constant is 29.4 atmosphere per molar, and so this comes out to be a 0.068 molar. So that's the concentration of CO2 in the solution when the pressure of CO2 above the solution is 2 atmosphere. Now, what assumptions are used in making this calculation? Well, we're assuming we're at Henry's law, and recall that if we look at the partial pressure as a function of mole fraction of some component, here we're going from 0 to 1, and in general for gases we have non-ideal behavior. So let's say we have something like this. So what we're assuming is that we're low enough concentration down here. This would be Henry's law. Remember Henry's law, you draw a curve tangent to the data at low concentration and say that the pressure is proportional to mole fraction, or in this case concentration unit molar, proportional down there. So that's the big assumption, that we're low enough concentration so that pressure and concentration are proportional with the given Henry's law constant. What reactions in water could occur to make this calculation ambiguous? So carbon dioxide as a gas can dissolve in water. These are all equilibrium steps to make carbon dioxide aqueous. But then there's a chemical reaction that occurs, carbon dioxide with water, to make carbonic acid, which then dissociates into at a neutral pH, H+, and a carbonate ion, HCO3-. In fact, it's because of this reaction that the pH of water exposed to the atmosphere is about equal to 5.5. So it's acidic. It's acidic because carbon dioxide dissolves and produces protons. All right, so when it asks for what is the molar concentration of CO2 in the solution, are you talking about just this, so the CO2 gas in the solution, or are you talking about all forms of CO2, including the CO2 that went into the solution as carbonic acid and now sitting around as carbonic acid and bicarbonate? So it's a little ambiguous what you mean by that, and you have to look carefully at what Henry's law constant they're talking about. All right, let's do another example. A solution is made by dissolving 75 grams of sucrose in 900 grams of water, 25 degrees. The vapor pressure above the water is 281.9 millimeter mercury. The vapor pressure of pure water is this. What's the activity of water in the solution, and what's the activity coefficient of water in the solution? All right, so let's just draw a picture of what's happening here. So what we have down here is water and sucrose that we dissolve, so it's aqueous sucrose. And then up here what we have is just water. Sucrose does not have an appreciable vapor pressure, so the only vapor above here from the solution is water, not from sucrose. All right, so for this system, the activity of water will be the pressure of water. This is the activity of water in the solution. Will be the pressure of water above the solution up here divided by the pressure of pure water. All right, given in the problem, the pressure above the solution is 281.9 millimeter mercury, and the vapor pressure of pure water is 289.1. So the activity of water in the solution down here is 0.9751. Okay. So what is the activity of water in the solution? What is the activity coefficient of water in the solution? That's a little more challenging problem. But we know that the activity of water in the solution will be the activity coefficient of water in the solution times the mole fraction of water in the solution. So we can figure out what the mole fraction of water is in the solution. We know what the activity is of the solution, and we can compare those two. And if gamma is 1 and they're the same, the actual activity, then the activity coefficient is equal to 1. If they're different, then the activity coefficient is not equal to 1. All right, so let's go ahead and look for the mole fraction. So the mole fraction of water in the solution is equal to the number of moles of water in the solution divided by the number of moles of water in the solution plus the number of moles of sucrose. The number of moles of water in the solution, the mass of the water was given as 900 gram. The molar mass of water is 18.02 gram per mole. So this comes out to be 49.94 mole. That's how many moles of water. The number of moles of sucrose given in the problem, we had, what did we have for sucrose? I forgot. 75 grams of sucrose. We'll put 4 significant figures there. The molar mass of sucrose is 180.1, I think, gram per mole. So the moles of sucrose in there is 0.4163 mole. So the mole fraction of water will be the number of moles of water divided by the total moles and the mole fraction of water. The actual mole fraction that you made up the solution is 9916. Okay, so that's the actual mole fraction. The activity here was 0.9751. So the activity coefficient of water is equal to the activity of water divided by the mole fraction of water. We have the activity of water. Here we have the mole fraction. Oh, look, it's different. So if the activity coefficient for were 1, the activity of water should be the same as the mole fraction of water. It's not, so therefore the activity coefficient is not equal to 1. And we'll just calculate out what the activity coefficient of water is in that solution. That is the actual activity, 0.9751 divided by the mole fraction, 0.9916. So the activity coefficient of water is 0.9797. Not quite ideal solution. The activity coefficient is less than 1, meaning that even though you have 0.996 mole fraction, the activity is less than that. So it's as if water is less active than you would expect for its mole fraction. Okay, so that's it for examples.